This will be a quick video here. We're going to do one more instant center problem. So for this one, I'm dealing with what looks like a pulley, but it's a spool. So picture we have a spool which basically has two parts. A larger radius spool that's wrapping the rope that produces E falling off, and a shorter radius spool that's connected here to the ceiling. So, and these things all rotate together. So, and critical points are noted. So, we're going to assume here that the ropes all hang vertical, so there would be, due to mass here, mass there, there would be a slight shifting, but we're not going to worry about those that geometry. So we're going to assume these are sufficiently long that these are all vertical, and we're going to allow. Oops. So we have angular velocity going counterclockwise. This is going to be unwrapping like so. That should be obvious. This distance A to B is 0.1 meters, and from B to C is 0.15 meters. So hence B to D would also be 0.15 meters. And so the question is how fast is E going down? And the key to doing this problem is an instant center. It becomes a joke. So what on this problem is not moving? Well, as this rolls down, this is just hanging. This has no velocity. So as something comes off of this smaller spool and it then unwinds off, okay, this becomes a point of zero velocity all along here. So if you really look at what's happening, it's kind of like this is a road going down, and this wheel here is just rolling down the road, okay? In any case, you should be able to see that A is the instant center. This has zero velocity, which means at this instant, everything is rotating relative to that point. Okay? So, if this is zero, well, it says I'm rotating about here, so all I need is this distance to here plus this distance to there, and that'll determine the velocity at D. That's all there is. So what is this distance? Well, it's 0.1 plus 0.15, so it'll be 0.25. So I have the radius at 0.25 times 4. That says this is 1 meter per second down. And if we go take a look at this, bring all this up, that's exactly what we have. Straightforward. Okay, we're now going to be moving into relative motion analysis, which is going to be involving a lot of one concept all over the place, and that's going to be cross products. And so I just want to comment, when I go to do cross products, you'll often find on the piece of paper that I write the following thing down. So this is just a quick tool, because picture you're seeing vectors where you're going to have x cross y, z cross y, z cross x, and keeping those all straight and figuring out how to do that can be really, really hard. And it can be confusing. On an exam, you get them all mixed up. Here's how I eliminate that problem. If I have cross products, generally at the top of the page I write the following: x, y, z, x, y. And so what does this do? Well, it's simply, you'll notice I have going, if I read this in the normal way, so left to right, so normal, I'll call that positive. So what that says is x cross y gives z, y cross z gives x, z cross x gives y. If you read it backwards, we'll call that negative. Okay, y cross x is minus z, x cross z is minus y, z cross y is minus x. So as you're going to do cross products, use this. Just write it. As soon as you realize I got to do cross products, I'm going to be setting up vectors and doing cross products all over the place. Write this down, and so then as you're having expressions where you have all sorts of things cross producting, you just go and check against here. You can't go wrong. It's the way that I've done it for years, and it's served me really well. I hope it helps you. We'll talk to you later.